Imagine a packet had just arrived at your computer. The network layer has done its job getting it there, but now it faces a critical question. Who do I give this to? Is this data meant for a web browser using TCP or a video stream using UDP? The network layer doesn't look inside the payload. It relies entirely on the IPv4 header to make that decision. Today, we are decoding that header. It's not just an address label, it's the instruction manual for how to handle, fragment, and deliver data to the right transport layer process. It's the instruction manual for how to handle, fragment, and deliver data to the right transport layer process. Today, we're breaking down the header, the part of the packet that tells the network where to go and how to get there. This is the IPv4 header, and the payload comes after that. The header usually consists of a 20-byte fixed part, plus optional variable fields. Let's read this row by row from left to right. First up, the version. For IPv4, this is set to 4. This allows networks to handle transitions between versions like IPv6. So we're talking about IPv4, and this is set to 4 obviously, as IPv4 means IP version 4. Next is IHL, Internet Header Length. Because the header size isn't constant, this field tells us how long the header is in 32-bit words. The minimum value is 5, which means 20 bytes. So it tells us how many rows we have. The minimum one is 5, signifying 20 bytes. So each row has 4 bytes, which is 32 bits. And times 5, 4 times 5 is 20. So the minimum number here is 5, telling us that we have 5 rows, which are 20 bytes. And what about the maximum? The maximum number we could put here, since it's only 4 bits, is 15. So 15 tells us that we have 15 rows, and each row is 4 bytes. 15 times 4 is 60 bytes in total. So we have 20 fixed bytes at the beginning and 40 bytes for the options. Then we have the differentiated services. Originally, it was called type of service. It was only 6 bits. This was meant to prioritize traffic, like choosing between speed or reliability. Today, the top 6 bits mark the service class, and the bottom 2 are used for explicit congestion notification. So the top 6 act as it was the type of service previously, and then those 2 that were not used initially are for congestion. Finally, for this row, total length tells us the size of the entire datagram, header plus data. The maximum size is 65,535 bytes, which is 2 power 16 minus 1. How did we reach that? The total length part is 16 bits, so the first one is 0000, so the last one will be 2 power 16 minus 1, which is 65,535 bytes. The second row is all about fragmentation. Sometimes a packet is too big for a network to handle in one piece. Identification. This number helps the destination put all pieces of a fragmented packet back together. Next, we have our flags. We have 2 key bits here. The don't fragment, or DF, tells the routers do not break me apart. And the other one is MF, or more fragments. It's set on every fragment except the very last one, so the receiver knows when it's done. So we have many fragments. Each one will have this MFB1, except the last one will be 0, so the receiver knows when it's done. Next is fragment offset. This tells the receiver exactly where this specific piece belongs in the original packet. Note that this offset must be a multiple of 8 bytes. Now it's row 3. Row 3 is critical for routing and safety. First is the TTL, or time to live. This isn't time in seconds, but a counter of hops. It's decremented at each router the packet passes through. If it hits 0, the packet is discarded. This prevents lost packets from wandering around the internet forever. So for example, if router A, router B, router C. This is the normal route, and if something happens leading to router B thinking that the shortest path is sending it through A, and then A will send it to B, and then it will just keep going back and forth. This is an example when TTL is useful, as after a specific number of hops, it will just discard the packet instead of wandering around in the network or the internet forever. Next is protocol. Once the packet arrives, who gets it? This field tells the network layer whether to hand the payload to the TCP, UDP, or another process. Then, the header checksum. This verifies that the header hasn't been corrupted. Crucially, because the TTL changes at every single hop, this checksum must be recomputed by every router along the path. Finally, addresses and options. Rows 4 and 5 are the source and destination addresses. These are your standard 32-bit IP addresses. Finally, we have the options field. This is variable length and helps path the header to a multiple of 4 bytes. It can include things like strict source routing, listing the exact path a packet must take, or record route, asking routers to sign their IP addresses as the packet passes. Timestamp, asking routers to record when they saw the packet. However, because the max header size is 60 bytes, there's only space for about 40 bytes of options, which makes features like record route limited to just 9 hops. And that is the IPv4 header, a 20-byte roadmap that guides the internet. If you found this helpful, subscribe for more engineering breakdowns.